There's something unusual that happens with refraction. And this video we're going to talk about it is total internal reflection. Now we saw from Snell's law in this slide here from earlier that the index of refraction times the sine of the incident angle is going to have to equal the index of refraction of the second material times the sine of the refracted angle. That's the Snell's law. Now, if the second medium has a larger index of refraction, so for example you're going from air to water, then you're going to have a smaller angle. However, if you go from some medium into a second medium with a smaller index of refraction, then your angle has to increase. Let me show this to you here. So here we have a laser shining from air into glass. And so sure enough, I shine the laser, it bends. Light is going from one angle, and then the refracted angle is going to be smaller. Again, that's exactly what we saw here. If we go from one medium into a second medium, with a higher index of refraction, the angle is smaller. And that's exactly what we see here. And of course, I can move my laser around and I get any refracted angle. My incident angle can be anything from 0 to 90, but my refracted angle can only reach a maximum value. But if I switch this around and I go from a higher index of refraction to a lower one, then like we saw here, if you go from an index of refraction to a lower index, then our angle needs to increase, which is what we see here with you have an incident angle and then the refracted angle increases because you're going from a larger index of refraction to a smaller one. Now here's what's unusual. I can go up to an angle of 0 and it works. I get a refracted angle. But since the refracted angle is larger, then at some point I get as high, I went too far, there it is. I get as high as I can go. In other words, I get a refracted angle of 90 degrees. After that, well, I'm refracting more than 90 degrees. That puts it back into the glass, in which case you stop refracting completely and you start completely reflecting. So if light passes into a medium with a smaller index of refraction, so from a larger to a smaller, then you get this total internal reflection, and this angle where this occurs is called the critical angle. So the sine of the critical angle would be n2 divided by n1 times sine of 90 degrees. In other words, sine of the critical angle is just equal to n2 over n1. So here's another picture showing what's going on. N1 is smaller, N1 is larger, N2 is smaller. So this would be going from glass to air, glass to water, water to air. Any of those would work. Perhaps you've seen this in a fish tank. If you look in the sides and the back of the fish tank, you'll often see reflections inside the fish tank. Why? Because light comes and can refract. Let me get a better color here. Light can go and refract, but as the incident angle increases, the refracted angle increases even more, and eventually you get to your critical angle where your refracted angle is 90 degrees. Anything past that critical angle, you obtain total internal reflection. Now this is really helpful in optics. We like to use mirrors. Mirrors are great, but when you need precision instruments, such as in astronomy, even mirrors are not 100% reflectors. They don't always reflect 100% of the light. They often absorb some or even refract some. But if you can arrange mirrors such that they're above the critical angle, then you get total internal reflection. Then you do get 100% reflection. You don't get any loss at all. And so often in things like telescopes, they do use mirrors, but they use mirrors and total internal reflection to maximize the amount of light. Where else can we see this? Something called fiber optics. The idea is you have a cable, and this cable, you have light that comes in at a very high incident angle. High enough that it's past the critical angle, and so you get total internal reflection. Bounces back. Hits the other side of the fiber. Same, very nearly the same angle, and so it just bounces back and forth and back and forth. And so you can take some image over here, take this image on the bottom right, and then put a cable in front of it, and if this thing is shining light, that light is going to bounce back and forth all the way through the tube, so that on the other side of the fiber optic cable, you have an image of what you initially started with. Now, this creates an awesome possibility where you can get pictures inside of somebody's stomach or esophagus or whatever. So here you have a doctor looking down into someone's throat. They have a fiber optic cable that is going down into the lady's throat, and he can see what's going on. How? Because any light that is being shined into the throat bounces up the fiber optic cable all the way through the fiber optic cable into the computer system where he can see a picture of what's going on.